So our next speaker is Babak Hassibi, who's going to speak about subspace expanders and low-rank matrix recovery.
Okay, is this working? Okay, well, thank you for the introduction. It's certainly a pleasure to be here. So what I'm going to talk about today is some work that goes back almost a year with my graduate students, Samit Oymak and Amin Khajanejad. And, you know, I haven't had really the opportunity to ever present this work, and so I figured, you know, this is as good as any other one. And so it really came out of a curiosity. And the work is a bit speculative, but I hope it'll have some aspects that might interest some of you. So I'm going to talk about subspace expanders and relations to low-rank matrix recovery. So here's the outline. So I'll say a few words about expanders. I'm sure many of you are familiar with them. And I'll talk about how they come about in coding and compressed sensing. And then really what I want to do in this talk is to see whether those ideas can be taken and generalized to matrix problems, in particular rank minimization problems of that sort. And so we'll look at, you know, an extension of conventional expanders that we call subspace expanders or rank expanders. So I'll define what they are, and I'll prove that some such objects really exist. And then we'll look at, you know, applications to low-rank matrix recovery. I'll describe something that looks like a fast algorithm, perhaps, and then kind of speculate as to what all this means. Okay, so what is an expander? Again, I'm sure many of you are familiar with this. So think of a bipartite graph. So you have nodes on the left and nodes on the right. And so an expander is a bipartite graph. It's described, I guess, by 5 parameters. So you can think of n as being the number of nodes on the left, m being the number of nodes on the right. The nodes on the left are sometimes called variable nodes. The nodes on the right are called check nodes. And then these are often, if you will, left regular graphs. So if you look at the number of edges coming from every node on the left, it's a fixed quantity d. That's called the degree. So you have a constant degree on the left. And then the important property is the fourth one that I've lit there, is that, you know, if you look at subsets on the left of nodes of a certain size k, as long as this k is less than n alpha, so alpha is some parameter less than 1, so if the sets are not too big, they have to expand to large sets. They have to have a lot of neighbors. So in particular, if you have, say, k, I don't have a pointer here, but if you have, say, a set of size k, the number of edges emanating from this set is k times d. So that's the maximum number of neighbors you potentially could have. And so what we want is to have at least some fraction of that. So 1 minus epsilon times dk. And so epsilon represents the expansion. The smaller epsilon is, the more expansion we have. Okay? So this is called an expander. Essentially, sets on the left get expanded to large sets on the right. Almost, you know, if epsilon is small, almost to the maximum amount they can. Okay? And so expanders were, I guess, introduced in the 70s by Pinsker, looking at some network problems, network flow, and things of that sort, mixing times and so on. And so it's known that such things exist. In other words, you can have graphs with this property. In particular, if you generate a random deregular graph, it turns out with high probability that they're expanders. And people have actually gone about and looked at explicit constructions of these things. In the old days, they used Cayley graphs and so on. Nowadays, there are explicit constructions. I should say explicit in quotations, because it's kind of CS-type constructions. But you can have constructions for expanders all the way to epsilon very close to 0. So things that really highly expand. So these things you can actually construct. Now, why are they useful? As I said, they, you know, originally came up in network problems, but they're of particular interest in coding and compressed sensing. And so let me say a few words about that. So if you look in coding, if you look at the adjacency matrix of this expander graph, so think of it as being, you know, an m by n matrix. you can view it as the parity check matrix of an LDPC code, for those of you who know what that means. So if you look at this, again, bipartite graph, the nodes on the left you can think of being actually the code word, the variable nodes, and the parity checks are the nodes on the right. So those are the parity equations, say, that the components of your code word needs to satisfy. And it turns out that if you have an expander, then there are very efficient ways of decoding these. There's an algorithm called bit flipping due to Sipser and Spielman. Spielman won the Nevanlina Prize, I guess, last year, and it was partially for, I guess, this work. And you can also do linear programming decoding. So it comes up quite naturally in coding. In compressed sensing, it turns out that you can view, again, the adjacency matrix of an expander as your measurement matrix. So you have some sparse vector x living in ambient dimension n. So again, going back to this picture, you can think of the nodes on the left as being the components of your sparse vector. And you make a measurement, which is a times x, again, looking at this picture. So you're basically measuring linear combinations of the entries, but they're sparse, and they're represented by the nodes on the right. Okay, so you may want to do this. Again, you might ask why, but it turns out that there are applications where these sparse measurements make a lot of sense. So originally, when we had looked at, using expanders, we were looking at DNA microarrays, and so kind of related to the talk earlier, basically a DNA microarray is a chip. It has spots on it, and each one is designed to capture a particular type of gene. And so you take biological samples and you label them with fluorescent molecules. And so it's very similar to what was mentioned in the earlier talk. The problem is that I think humans have 30,000 genes. And so a typical gene chip, if you will, has 30,000 spots. Whereas when you make if you're using diagnostics to detect, say, a tissue that's not healthy, typically all 30,000 genes are not differentially expressed. It's some small fraction of them, perhaps a few hundred. And so we were looking at, it looked like an ideal situation to use compressed sensing type ideas, to reduce the size of your array from 30,000 maybe to a few thousand. The problem was that you can't do general random linear combinations. It's very difficult to build arrays like that. And so we were looking for measurement matrices that were sparse, that had, say, only 5, 6, 10 non-zero entries in each row. So each measurement was just a linear combination of a very few elements of X. And there are other applications where this is quite natural to do. In addition to that, so it turns out that what matters if you look at being able to recover sparse signals from these expanders is how high the quality of expansion is. In other words, how small epsilon is. And so it turns out that, if epsilon is less than a fourth, you can essentially extend the bit flipping algorithm of Sipser and Spielman to the compressed sensing case. And the benefit is that it's a very fast algorithm. It works order n, so it's much faster than L1 minimization or anything like that. And because you have an expander, it has deterministic guarantees. And there's also a lot of subsequent work on this. It's known that these expanders have nice RIP properties. That's the work of Indic and others. Okay, so let me just briefly say a few words about this bit flipping algorithm, perhaps, so you get a sense of, if you have an expander, how quickly you can do things. So suppose you have some expander with expansion less than a fourth and some unknown signal of sparsity k less than n alpha, okay? And we want to recover it based on measurements y equal to ax, okay? So given an estimate of x, which I'll call x hat, you can look at the residual between y and ax hat. That's the error in your current estimate. And I'll just call that residual g here, and I'll call the ith component, say, the gap. If I have, it's the gap between the actual measurement and, say, what our estimate is. And so the algorithm is very simple. It's a greedy algorithm. You start off with 0. At any point, if you are able to get y equal to ax hat, that's the solution. If not, what you do is you look at the variable nodes. And each variable node, because you have a regular graph, participates in D equations. That comes about from this picture here. And so you look for a variable node which has the property that more than half of those equations have the same gap G. I don't know why this looks crazy, but once you find a node like that, you just basically update it. So this equation should say x hat goes to x hat minus g, and then you go to, so you just subtract g from that particular x hat that you found, and you continue until basically y becomes equal to ax hat. So the critical thing about expansion is that it guarantees that step 2 can always be done, so you'll find such an xi hat. And the reason why the algorithm is greedy is because if you look at xi hat, it participates in D equations. And if more than half of them have a constant gap, if I remove that gap, I'm basically setting more than half of those equations equal to 0. The other ones I might screw up, but what it really means is that I'm reducing the support of y minus ax hat, because I'm satisfying more than half of the equations in which it participated. And again, I won't go through the proof, but expansion basically allows all this to work, and you do everything in order n. Let me describe another fast algorithm that uses expansion. For simplicity, I'll do this for the case where the signal is non-negative, but you can generalize it. And so again, A is the adjacency matrix of an expander graph. You observe y equal to ax, where x is non-negative. And so once you do that, if you look at y has 0 entries and non-negative entries, or positive entries, if you will. And so basically what you do is you look at, say, well, I'll go right through this. You basically look at the zeros you get in y, and therefore their neighborhoods. So you look at all entries of x that are connected to a 0. Those entries of x for sure are 0, because there's no other way that you can get a 0 on the right unless it's connected to all zeros on the left. Okay? So you can determine a whole bunch of zeros on the left-hand side, and you're left with the green nodes on the left. And you don't know what they are, but the interesting thing is that if your expansion is below 1/2, you can show that the system of equations that you get from the green nodes, so viewing the green x's as unknowns, is overdetermined. And so you can solve it. You just solve a system of linear equations. So once you rule out the guys that are 0, what you're left when you have an expander gives a system of equation that's no longer underdetermined. It's overdetermined. So it's you just do one matrix inverse and you're done. Okay, so that was kind of a motivation to show that expansion is a useful concept in compressed sensing. And so what we're interested in this talk is whether we can extend this idea of expansion from compressed sensing to low-rank matrix recovery, and in particular to see if there's any algorithms that we can use. And so the main contributions are actually, we prove that such rank expanders exist, and I'll describe an algorithm. Again, I don't think in this audience I need to motivate this much. I mean, low-rank matrices come up in a lot of problems. They come up in system identification problems in control, and learning, and graph clustering, collaborative filtering like the Netflix problem. Again, it's an example of classes of problems where, the ambient dimension is high, but we're searching for a low-dimensional object, in this case, a low-rank matrix. Okay, so mathematically, what is the problem? So we have some matrix X naught, which is low rank. Yeah, I don't know why I'm getting these Chinese fonts here. And we make some measurement Y naught. So A is some linear operator. It just measures, entries or linear combinations of the entries of X, and we want to recover it. So we want the minimum rank X subject to those measurements. And the problem is hard because the rank function is non-convex. And so the approach that's been used is to relax it. And so this is supposed to be the nuclear norm. So rather than minimize the rank, you minimize the nuclear norm of x, which is the sum of its singular values subject to that constraint. And this is a convex problem. It looks like something that people should have looked at for a long time, but I think, it was first done in Maryam Fazl's PhD thesis some 10 years ago. And so people have looked at this problem, and there's typically two types of measurements that people have analyzed. One is related to the matrix completion problems, where you essentially look at certain entries of X and want to find the lowest rank matrix consistent with the entries that you've seen. The Netflix problem falls under this. Another class of measurements that people have analyzed is when your measurements are essentially inner products of some random IID matrix AI with X naught. So basically you multiply AI with X naught and then take the trace. The reason why people study that class of measurements is that it's manageable to analyze the behavior and the number of measurements you need and thresholds and things of that sort. So that's the work of Recht and Carrillo and others. Okay, so that's been quite a bit analyzed. Now, if you think about it, however, measurements like that seem unreasonable. If you have a matrix, making a measurement that somehow is a linear combination of every entry in the matrix doesn't make a lot of sense. I don't know of any applications where it comes about. And so more interesting might be a situation where our measurements are linear combinations of only a few entries of the matrix. So this is something in between looking at actual entries of the matrix and forming linear combinations of all of them. And so the question is, how can one construct such measurements and devise algorithms? And we'll do this based on the notion of expanders. So how will we go about doing this? So when we looked at expander graphs, we were mapping, if you will, n nodes to m nodes, or n-dimensional vectors to m-dimensional vectors. And so here what we're going to do is we're going to take n by n matrices. So for simplicity in this talk, I'll look at square matrices and, in fact, symmetric ones, though that doesn't matter. And I'll map it to m by m matrices. So m is smaller than m. So I'm taking a big matrix, I'm mapping it to a small matrix. And what do I want of this mapping? Well, again, I'm trying to do an analogy with the picture we had, say, over here, where our expander graph had constant degree. And so what that means for graphs is that if you have any vector of support 1, it gets mapped to a vector of support D. So here I want all rank 1 matrices to be mapped to rank D matrices. That's the first thing I want. And then after that, I want expansion. So if I have a matrix of rank R, I want it to be mapped to a matrix of rank at least dr times 1 minus epsilon. Because dr would be the maximal rank, say, it could be mapped to. Okay? And I'd want other things. I want to preserve positivity. If the matrix is positive semi-definite, I want the mapping to respect that. Okay, and so here's the proposed operator that we suggest. So I'm going to start off with D matrices, A1 through AD, and these are m by n. So m is smaller than n, so these are long or fat matrices, if you will. And I'm basically going to look at the sum of AI x AI transpose. Again, I'm doing this because I'm assuming x is symmetric. I need not do that. And this is a reasonable choice because if I start off with a matrix that has rank R, the rank of this thing, because it's the sum of D potentially rank R matrices, the rank is at most dr. It preserves positivity. And the idea is if, the D matrices that are adding up, if they're sufficiently incoherent, the rank should add up, to something large. Okay? Of course, things are a little bit more complicated because maybe they don't add up, or maybe some of the dimensions of the X get killed by AI or whatever. It's a little bit more complicated, but it looks like a reasonable choice. Okay, so here's a picture of what the structure is. You're taking your X, you're pre and post multiplying by these matrices and adding them up. And so if you want to think of it as a graph, the nodes on the left, if you will, are all rank 1 matrices. So X is equal to VV transpose. And the neighbors are just rank 1 matrices, A1 VV transpose, A1 transpose, all the way to the dth one. Okay? Again, the complication here is that potentially some of these rank 1 matrices could be 0, but I don't want to go into any of that. So the only difference really, if you will, is that your rank 1 matrices now form a continuum. But I do want expansion for all of them. So here's the, I'm sorry about this. So the definition of an expander. So I'm looking at an operator that's supposed to map n by n to m by m matrices. So I'll call it an epsilon d r naught rank expander if it's basically if the rank of a of x, I'm sorry for how the last equation shows out, is bigger than 1 minus epsilon rd. It's the usual assumption. And so the theorem that we have, just to give you a sense of why this expansion could potentially be useful, is that if I do have an expander like this with, say, expansion less than 1/2, then it turns out that any positive semi-definite matrix X naught of size n what is this saying? So it's basically saying that there's only a unique X naught that satisfies the equation, say, y equal to ax naught, and is positive semi-definite if the operator A is an expansion. Oh, this is ridiculous. Okay. I really apologize for this. We did check the equations, but not the last ones. Essentially, the algorithm says that, as long as you find any non-negative solution to the equation, it's the low-rank solution that you want if you have an expander. We have an existence theorem, which basically says that if I choose as my matrices the AIs just IID Gaussian matrices, then they're constant C1, C2, such that for any epsilon, if you set M to something proportional to n times the rank, and D, the number of matrices, to something like the ratio of n over n r naught its square root, then with high probability you'll get an expander. And again, the proof is boring technical stuff that I won't go through. And you can argue that the numbers that we get here are kind of order optimal in terms of the fact the number of measurements we require is consistent with the number of degrees of freedom of a rank R matrix. Okay. So basically where we're at is if we take IID Gaussians for our A's, in fact, we do get an expander with high probability. And so maybe I won't go through the details, but we can give a fast algorithm now for recovering X from a measurement of this form. And it's really the analog of the algorithm that I had here, which involved essentially identifying the neighborhood of the zeros of y and then solving a linear equation for the rest of the x's. And so it turns out that when you have expansion, you can do the exact same thing for matrices. So essentially, you look at your y, you do its SVD to determine the subspace of y, then you determine P, which is the orthogonal complement. So it's kind of the where y is 0. The next calculation essentially finds the neighborhood of y. And then again, I'm skipping the details. And so once you've found the neighborhood, you essentially have found a basis for x. And after that, it's just solving a system of linear equations, which is the equation I have at the bottom there for x. It involves a pseudo-inverse of a certain matrix M. But essentially, the problem then becomes one of just matrix inversion. And there's a theorem that goes with this, basically saying that if you have expansion less than 1/2, for every rank k less than r naught times 1 minus epsilon, the algorithm I just described will recover the low rank matrix. I have some simulations here just to show all of this. So this is a 50-dimensional example. So we're looking at a 50 by 50 matrix. The red curves are nuclear norm minimization. The blue curve is the fast algorithm I just described. The y-axis is the sparsity, that's k. The x-axis is m, the dimension of the smaller matrix. So the original matrix is 50 by 50, so there's 2,500, if you will, entries in it. M is running from 15 to 50, so for example, when m is 30, we have 900 measurements out of the 2,500. And you can look at the curves to see what value of k you can recover. And then I guess the curves are for d equal to 2, d equal to 3, and d equal to 4 in terms of the number of matrices in the summation. We've looked at two different ensembles for constructing A. One is a Gaussian ensemble, and so those are the curves that go smoothly, down. And we've also looked at a sparse construction for A, where basically each matrix AI has only one non-zero in each row, and we randomly chose that. And so for those sparse matrices, if you look at the curves, at some point they depart from their corresponding Gaussian ones and basically hit 0, meaning that if your matrix AI is too sparse and random, it's no longer an expander. Okay? So we perform almost as well as the nuclear norm minimization, but the algorithm is an order or 2 orders of magnitude faster. Okay. So that's the simulation. Let me just mention a few words about future work. So the results we have and the theorem we have are for these Gaussian AIs, and things are nice theoretically and computationally, but they're not very reasonable measurements because again you're forming linear combinations of every entry of the matrix. And so we've looked at sparse measurements. And they don't seem to work very well unless m is large, and so I think we need a more systematic construction, just random, sparse, just one non-zero entry in each row of the AIs doesn't seem to work. One can do an analysis in the presence of noise, and we're also interested in whether there's a counterpart to bit flipping. Again, if there's interest, I can say a few words about that, but we don't know how to do matrix bit flipping at this time. Again, as I said at the beginning of this talk, this was all very speculative. We were trying to see if we could extend expansion to matrices and get anything. And so the question is whether these measurements come up anywhere. One possible area could be in quantum measurements, trying to estimate quantum states, because there it turns out that your measurements are basically, you compute inner products with Pauli matrices, which only have a few non-zero entries, and so we feel there's a strong connection to this. But we don't know of other applications, so I'll stop here. Thank you.
So we're running a little bit late, so maybe just one question while we get set up for the next speaker.
Yeah, so that's a good question. So the algorithm I described, and even its counterpart in the usual expander case, is fairly resilient to noise, because rather than make a decision about where the signal is 0, you can look at where it's small, or in the matrix case, you can do an SVD and kind of determine where the signal and noise subspaces are. Whereas the bit flipping version is sensitive to noise. And so we've done some preliminary noise analysis for the algorithm I described.
Okay. Let's thank Babak again.